Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. Today we will continue with the understanding we got last time about multiparticle systems. First, we will build up on that by analyzing velocity and acceleration of the reference frames. Then we will treat center of mass of not only a system of particles but of a continuous system. Finally, we will see how a system of particles can be reduced to a point particle. So, let's start! Great, let's start with the velocity and acceleration on our reference frame. Recall we had this blob of particles and we had these little particles in them. And now we're going to draw our center of mass right around here, the center of mass. We had our stationary frame S, and we also had this RS comma J, and we had this RCMJ, and finally the vector we tried and found a formula for, that is capital R CM. If you recall from last video, we found that the video will be pinned over here. We found that RCM equals the sum from j equals 1 to n of mj times rs comma j over the total mass, that is the sum from j equals 1 to n of mj. Now we'll differentiate this and we'll see what we get to try to find the velocity of the center of mass frame. Differentiate and we get b of the cm equals ddt of all of these, and well, ddt, let's write it out, of the sum. I'll skip the different j equals 1 to n of all the sums because it's really tedious, to be honest, and the sum of mj. We can see that the ddt doesn't affect our sum of mj, the total mass. It doesn't affect neither that mj above, and it distributes over the sum. So it goes through till it hits this rsj, and we get that this is mj times b of s comma j over the sum over mj. Now we'll see what RSJ really is, and we'll find that it really doesn't depend on our reference frame S. If we define another reference frame, let's define it over here, P, we'll see that we'll have this vector capital RSP, and we'll have this small vector, I'll draw tilde there because I'm going to cross mg if not, that is going to be RP J, and we see that ddt of rsg, rs comma g, which is no other thing than a ddt of rs comma p, capital R, plus rp j, it's equal, because this is a constant and it vanishes, it doesn't change in time, that reference frame, it's equal to ddt of rpj. And therefore we can take these sub-indices of here, because in general this velocity is not going to depend of the reference frame, the stationary reference frame we choose. And this also has the implication that the b of the center of mass, the velocity of the center of mass, is not going to depend on the stationary reference frame or the arbitrary point S we choose as our reference frame in general. It's not going to depend on it. We can differentiate once more, and doing the same thing, we will find that the acceleration of the center of mass is equal to the sum. I'm going to go over here because it's weird to write from there, and AJ divided by the total mass. And this is the acceleration and velocity of the center of mass of a system. Great, now let's generalize this notion of center of mass to continuous systems of particles. Once again, we're going to have this blob of mass, but now it's going to be a continuous system. So instead of taking small mj particles, we're going to take small elements of mass such as delta mj. So we will symbolize that as, let's see, an arrow, and this is going to be our old multiparticle system mj, and now we're going to have, I'll draw it in red, the new continuous system delta m. Well, sorry about that, there's no j indices here, and this is going to work as a differential in the end, differential of mass. Now, instead of having a vector that is going to point to the particle, we are going to have a position vector. Imagine, for example, from this reference frame, that could be the center of mass frame, or, well, better off, because we are trying to define the formula for our reference frame, let's take it to be a frame S, independent of the system, and we are going to have a position vector that goes to delta m. So what used to be Rj now has become Rj or delta m, and it will become the position vector to the differential of mass. And then in physics in general, when you pass from a discrete system to a continuous system, usually you are involving sums, and we'll see that the sum of our system from j equals 1 to n, it's going to become an integral, a triple integral over the volume of the mass. And with these notions, we can rewrite the formula for our center of mass. We'll see that R Cm, that used to be the sum of R S comma J, well, this is S comma J, times the little mj over the sum of mj has become, see, that the center of mass, the new continuous center of mass, equals, we have a sum, so we get a triple integral over the mass of this vector and its differential, the m, and below here we get a sum once again, so that's a triple integral over m times the little differential of mass. And this is how you generalize the notion of reference frame of center of mass to continuous systems. Now we'll reach the climax of all of our multi-particle system videos, to this point in which we will generalize our system to a point particle. will make both systems equivalent. In general, we had this system, this blob of particles with particle 1, j, n, 3, n minus 1. And now we are going to treat this, we are going to transform it into a point particle, that is going to move along the center of mass trajectory. Recall from the previous video that we found that F external is equal to the change of the momentum of the system times over time, the time derivative. And recall also that this is the dt of the definition of the momentum. That is from j equals 1 to n of mj bj. And once again, as we have done multiple times in these videos, we see that the ddt goes through. This is only a revision of what we had from j equals 1 to n of mj aj. And now let's recall the formula we had for the acceleration of the center of mass from a previous segment of this video. This was the sum from j equals 1 to n of mj times aj over the sum once again of mj. But see, these two expressions are really similar. In fact, they only differ by this factor. And we are going to define this factor. This is going to be defined as mt, as m total, which is going to be equal to the sum of j equals 1 to n of mj. And we see that we have arrived to a final expression. All the work we have done has taken us here, and we see that the force external applied on our system of particles equals the total mass mt times the acceleration of the center of mass. So in fact, we can treat this system of particles, as long as they stay more or less together, as a point particle that is moving along the position of the center of mass with mass mt. And this is something we have been using for all of our physics career. For example, when we generalize planets as point particles. And finally, we have been able to justify this assumption. All this procedure can be taken to continuous systems just by doing the substitutions that we announced earlier. That is all for today. I hope you liked the build-up we have been making over the past videos so that we'd reach this climax in which we justify that assumption that we have been making since high school. I hope you liked it, and any doubts left, you may ask them in the comment section. Remember to like the video if it was the case, and press the subscribe button, the bell, and follow us on Instagram so that you don't miss any of the new videos. See you another day with more Physicawesome!